So you can just go to that YouTube channel and you can watch the lesson if you missed it. You can, again, like I said, I did put up the video of the test corrections process. You can use that to help make your test corrections. And then for test corrections, remember you need to do it on a separate sheet of paper. You need to include for multiple choice questions the correct answer and then some sort of statement proving to me that you know why that's the right answer. And you can take different routes. You might just explain why it's right. You might explain why you were wrong before, something to show me that now you know why that is the right answer. And then for the free response questions, just redoing the parts you missed. So if you only missed part D of the last question, you don't need to do A, B, and C. You just redo part D. And if you had a simple mistake, like on the first free response of maybe just missing a unit or not correct sig figs, you don't have to redo the problem. Just say missed sig figs should be, boom, you're done. Something like that. Then you'll submit those. Corrections are a separate assignment in Access, so you can submit it there. It doesn't go in as a grade there, so even though it shows up in the grade book, it doesn't impact your grade there. What it does is gives you the chance to earn the curve. So once, and I've actually just kind of been checking every other day. If I see that you've submitted your corrections, I check it and then go ahead and put the curved grade in. And I'll be doing that probably tomorrow while people are finishing up their retakes. You do have to do the corrections before you can do a retake. I had a few do it yesterday, and just two, and they both actually scored better the second time. I didn't ask them. I forgot to. I was going to see what their impressions are. My personal feeling is the multiple choice on the retake is slightly easier, partly because a section of it is so similar to what you've already done. You'll be better at it the second time around. And then the free response one is basically the same kind of a free response question, so I don't think it's any harder or easier. And then the other two free responses I think are a little harder on the retake. Not a lot, but just a little bit. So if you are doing the retake, make sure you do prepare. Don't come in cold just hoping you do better. Make sure you prepare so that you're in good shape to do that. But today and tomorrow at 4:00 p.m. Are the last two options since yesterday is done. So today at 4, tomorrow at 4. Those are your chances to do a retake for Unit 3 if you'd like. And just a reminder then, the unit test for Unit 4 is next week. And so for international students that are watching, you should schedule with me. I'm going to keep those same kind of timelines for you guys, Wednesday morning, Thursday afternoon, Friday afternoon, whenever we have a test. So international students watching the video, you can plan to come Wednesday at 8 a.m. next week to take it, or you can take it Thursday at 4 or Friday at 4 next week. For those of you that are in the on-campus classes, you'll just be taking it in class next Thursday for you guys and next Friday for B-Day students. All right, so that's all for reminders and introductions and timelines, deadlines, all that good stuff. Any questions about what's coming up? Okay, let's jump into the notes for today. Whoops. Oh, I wanted to show this again. I showed it last time, but I added a couple details. Like in the textbook, I added in writing. I said it last time, but I added it in writing that it's chapter 3 is the chapter I would encourage you to read. And you should probably pick that up if you read on Access what the questions are that I'm recommending, that they're all in chapter 3. I just want to emphasize that. And then the worked out examples that are at the bottom right-hand corner of the Unit 4 page in topics on Access. And then there's a few practice problems with answers there as well. But really the two that I think are most helpful are going to positive physics and just practicing problems. The more you can practice, the better you'll be at it. The Unit 3 free fall, we've already really tested over that, but free fall is part of projectile motion. And so that could help. But specifically Unit 4 on projectile motion, there's videos to help you. There's lots of problems to practice. Definitely recommend going through that positive physics for practice. And then the AP classroom, again, we are now wrapping up what they call Unit 1. All of kinematics and motion is their Unit 1. We've broken it down into segments. But now all the videos they have, all the topics, questions, and all the progress check questions should be relevant to you. You should have some idea about what they're asking, even if you're not quite sure how to answer it, because they're definitely tricky questions, high-level questions. But strongly encourage you, go in there, watch those videos, practice questions. You have a week to get ready for this test. And so use those opportunities. Use positive physics chapter or Unit 4. Use AP classroom questions and videos. All right, Almost forgot to do that, but I'm glad I put the slide in so it would remind me. Now on to the lesson. So projectile motion. In projectile motion, that for objects that are launched at an angle, I want to make sure that you understand that if we ignore air resistance, it's very symmetrical. We're going to see a pattern in the velocity that is helpful to think through. So if I'm launching this cannon at 40 meters per second and we're ignoring air resistance, it's going to slow down 9.8 meters per second every second, or basically approximately slowing down 10 meters per second every second. So after 1 second, it would slow to about 30, then 20, then 10, and then at the peak, it's going to have a vertical velocity of 0. It doesn't mean it's not moving. Okay? It will be moving horizontally, but it will have no vertical velocity at the peak. And then on the way back down, it'll be going at 10, and then 20, and then 30, and 40. So there's a symmetry to it. If it comes back down to the original height that it was launched from, then it's going to have the same magnitude, the same numerical value, or same absolute value as the original. It'll just be going in the opposite direction. Remember, for our vectors, the sign doesn't tell us the magnitude. The sign tells us direction. So we could put a -10, -20, -30, -40 on this right side of the parabola to show that they're downward. They've just left off the negative signs because visually you can tell by the context that it's downward. But the sign has nothing to do with magnitude. The sign is just direction. So we talked about this with the Unit 3 test review. If it talks about the magnitude, it's just saying basically what's the absolute value, because they're not concerning themselves with which direction it's going in terms of the negative sign. We do not, with vectors, think about a number line where negatives are less than 0. Negatives are greater than 0. They're just going the other direction. All right, so a little bit of a review on a few things there. Another thing that can be helpful is understanding it, and both the previous slide and this slide were touched on in that PhET activity that you did a while ago. So hopefully you've already sort of picked up on some of these details. But in projectile motion, the best angle to get the longest horizontal range is 45. Probably seems pretty logical, but you're maximizing the X component and you're maximizing the Y component. Well, you're not maximizing them individually, but you're creating an angle where they would be the same value. And so you're getting the most out of both, basically. That's where you can get the best out of both worlds, is at a 45 degrees. If you go 75 degrees, you're getting more value out of your vertical, but you're getting less value out of your horizontal. If you're going 15, you're getting more value out of your horizontal, but less out of your vertical. 45 sort of maximizes both. It's getting the most vertical you can while still getting the most horizontal you can. And so you get the greatest range when you use that 45. But complementary angles give you the same result in range. So 30 and 60 give you the same result in range. 75 and 15 also give you the same result in range. And any other complementary angles would as well. So again, this was something sort of touched on, but I wanted to dig in a little bit more in the PhET, but now formally in your notes to make sure you're getting that. However, this all assumes, both this previous slide and this slide, this all assumes we're neglecting air resistance, which we normally do. But I do want to have a bit of a reality check, even though we will normally ignore air resistance. I want you to recognize, hopefully, are you seeing, okay, it's just really slow. I'm watching on this screen here and it's really slow. So hopefully you do recognize that if there is air resistance, then we're not going to see those exact patterns because it will actually be slowed down. So while the ideal path would follow a perfect parabola, if there is air resistance, if we are taking it into account, it wouldn't reach the maximum height and it wouldn't reach the maximum range. And the shape of the curve wouldn't actually even be a true parabola. It'd be close, but not perfect. So while that's not really going to be something we apply, it's something you should understand fundamentally and conceptually. We're not really going to worry about the math of it, but you should understand it conceptually, that air resistance is a real thing and does throw our results off a bit. But the reason we typically ignore it is for most objects that don't get impacted by air resistance very significantly, our estimated ideal answer is pretty close. For those of you that have had chemistry, you probably learned about this with the ideal gas law, where the ideal gas law doesn't really tell you the exact value because there are going to be some intermolecular forces pulling them together, but it gives you a close enough approximation. Same kind of deal here. We're idealizing a lot of things, but it usually gives us a pretty close approximation because most of the time air resistance is fairly negligible. Not for all situations though. All right. This next part is actually sort of a preview of a couple units down the road. I think it's actually probably the unit we'll start right after Christmas break, and that is on circular motion. But it connects to parabolic motion, it connects to projectile motion. So I want to make sure that you're hearing an intro to it now. So Newton, we're going to learn about the universal law of gravitation that he came up with a couple months down the road. He had this thought idea based on his understanding of projectiles that if he stood on a high cliff and threw a rock off, at a low speed, it would go a low horizontal range. At a greater speed, it would cover a greater horizontal range. And if he could throw it even faster, it would go even farther. And his thought was, if he could make it go fast enough that the curve of this parabola started to match the curvature of the Earth, it would never hit the Earth, and it would just keep going. And so before we were able to launch satellites, he was already mentally processing how it would be possible with his understanding of projectile motion. Another way to view it is actually how he gave his thought experiment. He said, if I took a cannon to the highest mountain in the world and I shot that cannon, the cannonball would typically go a particular distance. And if you gave it more power, it would go a greater distance. And if you gave it more power, a greater distance. But if you could give it enough power, eventually it would miss the Earth. But that doesn't mean gravity wouldn't quit pulling it. Gravity would still be pulling it to the center of the Earth, but it would have so much horizontal velocity, it would just stay in orbit. So we'll come back to this and talk about it again when we get to circular motion and gravitation in the unit right after Christmas break. But I wanted to introduce it now because it connects to projectile motion. His whole thought came from understanding how projectiles increase range as you increase the velocity. So just an interesting thought experiment from Newton. All right, so now let's get into actual projectiles launched at an angle and the kind of work you're going to be doing in your worksheet and being tested over next week. So you've seen a bunch of diagrams similar to this now, but we've so far only looked at diagrams, or primarily looked at diagrams that were launched horizontally off of a cliff or something, or off of a table. Now we're saying, what if it's launched from the ground but upward at an angle? And so what we're saying is the actual velocity is this hypotenuse, or this angled red vector. And then that angled red vector changes, and then at the top it's only horizontal, because at the very peak it has no vertical velocity. And then as it comes back down, it's at this angle and at this angle. So it's actually a changing angle as it follows the path. But a few things we've already learned, and then some new applications. One thing we've already learned, the horizontal component, because we could find the horizontal element of this, the horizontal component would be constant. If we're ignoring air resistance, it would be the same vector. So you can see this Vox. Here they say Vx is Vox. So the horizontal velocity right now is the same as the initial. Up here at the top, Vx equals Vox. The horizontal velocity right here equals its initial horizontal velocity. And so the horizontal velocity doesn't change, since there's nothing to slow it down in that horizontal plane. But we could also find the vertical component of this angle. If it's moving at an angle, it has some horizontal movement, but it also has vertical movement. And so this vertical movement would be decreasing because of gravity. So when it's first launched, it would have the maximum amount of vertical movement at any point in its launching process. But as time passes, that amount would decrease because gravity would be slowing it down on the vertical plane. At the peak, it would have zero vertical velocity, and it would only have horizontal velocity at that instant. And then on its way down, it would be speeding up. And if it came back down to the height that it was launched from, its final vertical velocity would be the same in magnitude as its initial vertical velocity. It'd just be in the opposite direction. So all of those little details are important facts to remember. That the final vertical velocity will be the same as the initial, but in the opposite direction if it comes to the same height. That the horizontal is never changing in magnitude. And that at the peak, It only has horizontal because the vertical velocity would be 0. Now, we can see these little angled, the angled velocities, and then we can see the x and the y components. How do we find those x and y components if all we know is the angled velocity?
With trig?
Yeah, we're going to use the trig. If we knew this was 20 meters per second at 60 degrees, well, what trig function would I use to find the horizontal angle, or not the horizontal angle, but the horizontal velocity?
Cosine?
Cosine, because if it's a 60-degree angle, that horizontal side of it is adjacent. So we would use cosine. What would we use to find the vertical component?
Would that be sine?
Yeah,
Right?
yeah. It's opposite the angle, so we could use sine. Now, technically, we could use the actual hypotenuse and the horizontal once we found that. We could use tangent if we wanted to. But from the angle and the original value given, cosine would tell me the horizontal and sine would tell me the vertical. And that's what we're going to do. Let's look at another visual where this one just sort of takes off the actual velocity and only shows the components. And so in this case, we can see horizontally, if it had a 73.1 meters per second horizontal velocity, that would stay the same throughout the flight. But its vertical velocity, if it started at 19.6 in the upward direction, after 1 second, it would cut to 9.8. After 2 seconds, it would cut to 0, and it would only have the horizontal velocity. After 3 seconds, it would be at 9.8 in the downward direction. After 4 seconds, 19.6 in the downward direction, and so on and so forth, just increasing in downward velocity because of the acceleration due to gravity, because of the Earth's gravitational force field. So just visualizing it a bit different, only focusing on the components. This picture, though, shows us something. We won't always have the object coming back down to the same height. Sometimes it could get launched and fall down into a ravine like this picture shows. And so you have to be really careful about using signs for your displacement. So let's say that this ravine is 100 meters deep. From where it's launched, it's 100 meters down. What would my vertical displacement be? How would I write my vertical displacement if it's falling 100 meters? If it's falling 100 meters, what do I have to put on that number to make sure it's representing it as a vector properly?
A negative?
Yeah. We have to put it as a negative 100. So that's on the problems where it doesn't come back to the regular height, where it falls lower or lands on maybe like Batman movie. You throw the thing up onto the roof and then you climb up, right? So it actually lands higher than it was launched at. In those situations where it doesn't come back down to the same height, you have to think about the displacement. Launching a grappling hook up onto a roof, that's going to have a positive vertical displacement because it's higher than where it started. But launching it down into the bottom of a ravine, it's going to have a negative displacement because it ends up lower than it started. And so you do have to be careful with your signs on displacement when it doesn't come back to the same height. So just want to mention that as well. So any questions about what we've talked about? It's just been conceptual so far, but anything that you want to ask about before we do some practice problems? All right. So we're going to do 3 practice problems to kind of make sure you're getting the idea here. In this first example, it says, what are the maximum height and range values of a projectile if the initial velocity is 28 meters per second at a 30-degree angle? So how am I going to find my x and y components?
For the x component, you do cosine of 30 degrees times 28 meters per second.
Mm-hmm.
And then for the y, you do cosine of 60 degrees times 28 meters per second.
Okay. You could use cosine in both and use the complementary angles. or you could use sine of the 30 and get the same result. Either way would work. All right, so let's do that. To find the horizontal component, it's adjacent to this 30-degree angle, so I'm using cosine. Cosine of the angle is the adjacent over hypotenuse. So to solve for the adjacent side, I'd have to multiply both sides by the hypotenuse. That's why we're multiplying this 28 by the 30 cosine, cosine of 30. And it should make sense. So this 30 degrees means my adjacent should be smaller than the 28, right? I mean, it has to be less than the hypotenuse. So it's going actually 28 meters per second, but at an angle. So in terms of how it's relating to the ground relative to the ground horizontally, it's only moving 24.2 meters per second relative to the ground horizontally. Does it make sense? It's actually going 28, but relative to the ground, 24.2 in the horizontal plane. And then we could use the cosine of 60 to find the vertical, or we can use the sine of 30. We can stick with the same angle. The vertical would just be opposite the 30-degree angle, so that's why we'd use sine. And sine of 30 would be the opposite over the hypotenuse. So to find the opposite value, we have to multiply both sides by hypotenuse. So the hypotenuse is 28. So 28 sine 30 tells us the vertical component is 14 meters per second. Now, what angle would make these values equal?
$45.
45. If it was a 45-degree angle, then these velocities would be equal. And that's why the 45-degree angle gives us the maximum range, because it gets the largest values for both possible. So you don't have the vertical overwhelming the horizontal or the horizontal overwhelming the vertical. You have both of them maximized to get the most you can out of both simultaneously. Now, this is 30 degrees, which that's less than 45, which means my vertical should be less than the horizontal. At a smaller angle, it's going to have more horizontal velocity and less vertical. At a larger angle, it's going to have more vertical velocity and less horizontal, right? So these numbers make sense. And I would encourage you to always stop when you get these values and make sure they make sense, all right? They're both positive because they're both upward. It was launched at an upward angle, so the vertical and horizontal components we would consider are in the positive directions. Now, another thing that's drawn on this picture here is what they've highlighted here. The maximum y coordinate occurs when the Vy equals 0. In other words, it reaches its maximum height when the velocity in the y direction is 0. It doesn't mean it has no velocity. It would still be moving 24.2 meters per second horizontally relative to the ground, but it would have no vertical velocity at the peak. So knowing that it has no vertical velocity at the peak gives us a number we can use. We now know the initial vertical velocity is 14 meters per second. We also know at the peak, the velocity is 0 meters per second. So we know two velocities. What else do we know vertically?
Have we said acceleration due to gravity yet?
Oh, yeah.
Yeah, we haven't said that, and that is the third thing we know. Because gravity is going to slow it down on its way up and speed it up on its way down. Gravity is what's accelerating it. So we know two velocities, the initial 14 going up, the final at the peak 0, and the acceleration that causes it to decrease from 14 to 0 is 9.8 in the downward direction. So we know those three things. What equation can we use then to find the time?
The first kinematics equation, for like the velocity final equals velocity initial plus acceleration times time.
Yeah, good. That VVAT equation, that very first one we learned. So because we know the initial is 14 in the vertical plane, the final is 0 at the top in the vertical plane, acceleration is due to gravity, we can find the time. Now, you may be asking, Mr. Webb, the question doesn't ask us to find the time. So why would we do that? And there's a two-part answer here. One is we don't have to, not for this first part of the question. But the reason that I suggest finding the time is of all the variables, because just like we did in the horizontal projectile, we're going to separate the vertical and the horizontal. We're just like we did before. We're going to put the horizontal here. We're going to put the vertical there. We're going to calculate those things separately. There's only one variable that's the same in both for every problem. Occasionally you might see some crossover, but there's only one that's always the same, and that's time. And so generally speaking, you almost always have to find the time at some point in the problem. So I just usually try to find a way to start there. You wouldn't have to, though. Can anybody see a different route, a different equation we could use to find the height without knowing the time?
Using the one equation, you could solve for velocity final or velocity y final when it's 0.
Using which equation?
Hang on a second, sorry. I think it's the third one, the one without time.
The VF squared equals VO squared plus 2a delta x?
Yeah.
Yeah. So we could actually find the maximum height just using that equation, because it's got final velocity, which we know will be 0 at the peak, initial velocity, which we know is 14 vertically, acceleration, which we know is negative 9.8, and then the only other variable is the displacement, and that's what we're trying to find is the height. So we could just directly use that, and I'll show you that here in a few minutes. But generally speaking, for most of these problems, we're going to need to find time. So let's just start there, and then we'll show you both routes. So if we use VVAT, we've got Vy equals Voy plus GT. We're focusing on the vertical. Now, the reason we're focusing on the vertical is horizontally, we only know one thing. We know it has a horizontal velocity of 24.2 meters per second, but we don't know how far it's going to go, and we don't know how long it's going to take. So we really only know one thing horizontally. We know it's going to be constant, but we don't really know any other values. So we can't really start with the horizontal side. We really need to start with the vertical side. And so I focus in, I got to make sure if my initial and my final both have to be vertical. So my final is 0, my initial is 14, my acceleration is g, the acceleration due to gravity. I plug those numbers in, I solve for t, and I would find it will take 1.43 seconds to get to the peak. Any questions about that step? Now that I know it takes 1.43 seconds to get to the peak, how can I find the maximum height?
Just plug that in for t in the second equation.
Yeah. So let's show that. So here's everything we know. We found the horizontal and vertical velocities. We found the time it takes to get to the maximum height, to the peak. So if we use this second kinematics equation, and they're using y here. In the formula sheet, it says delta x, but they're just using y because we're focusing in on the vertical components, the vertical movement. Yeah, Nat typed it in here that's what we're going to do. We know our initial vertical velocity is 14. We now know the time is 1.43. We know g is negative 9.8. So we just plug in the 14 for our original velocity, the 1.43 for time, the negative 9.8 for g, the 1.43 for time. On this part, make sure we square it. We just multiply and add all that together, and we should get that the height is 10 meters. So that would be the approach of using the time. Now, it may seem like, well, Mr. Webb, we could have just solved it using the third kinematics equation faster. This took us 2 steps. We had to use VVAT to find the time, and then we had to use the second equation that we learned to find the height. And that's true. But I know, and hopefully you will begin to realize this quickly as well, maybe some of you already have, to find that horizontal range, I need to know the time. And so at some point I have to find the time to solve that part of the question. So using time right off the bat, finding the angle and the components right off the bat, that's generally a good strategy. If you're not sure where to start, find the components, use your trig first, just start there. Once you've done that, see if you can figure out the time. That's often going to be a next step that's going to help you. Once you start finding some pieces, if you keep your horizontal and vertical data points in lists on, I would suggest like one on the left side, one on the right side of your paper, you start to realize, oh, now I know the time. I can plug that in here. Oh, now I can do this. And it's like a puzzle. And I think that's part of the reason I love physics is so often when you're solving problems in physics, there's not one way to solve these problems. It's not like in a lot of math classes where you learn a problem and then once you know it, it's like repeat, wash, repeat, wash, repeat. Like you just keep doing it over, right? But in this one, it's like, okay, we've got all these tools. We have knowledge about parabolas. We've got knowledge about these kinematics equations. We have to figure out a path. How can I get from A to B using all these different tools I need? And I think because I love games, I love puzzles. And I think that's why part of the reason I love physics so much is like a little puzzle every time, trying to figure out how to put the pieces together. Now let me show you how we could have, to find that maximum height, just directly gone to the third kinematics equation. The third kinematics equation is this one, the VF squared equals VO squared plus 2A delta X. I've just substituted G in for A since the acceleration vertically is due to gravity. I know my final velocity at the peak is 0 meters per second. My initial velocity based on the trig is 14 meters per second. The acceleration is negative 9.8. I plug that in and I also get 10 meters. So there's multiple routes. There's not one way to do it. And the key is, can you find a way that works? All right. You don't have to do it the way I did it. You just have to find a way that works. And so it's a puzzle that has multiple solutions, or really one solution, but multiple routes to get there. But we're only done with half the question. We've only found the maximum height of 10 meters. Now we need to find the range. Whenever they use the word range, they're talking about the horizontal distance. So similar to range and domain in math, the range is that horizontal. All right. Let's see how we can figure that out. Any ideas? How am I going to figure out the range now that I know a few things here? Let's put together everything we know.
Just plug that into the D equals VT equation. So the time 2.86 seconds, and then our horizontal velocity of 24.2 meters per second.
Okay. And someone explain to me, Ethan got us started, somebody else explain to me, where does this 2.86 come from? Like, did I just magically pull that out of my hat? Johnny, you're shaking your head. Tell me, give me some feedback here.
It's the time that we found earlier doubled.
And why would we just double it? How do we know to do that?
Because the first time was just, and that has to also come down.
Good. Yeah. It takes 1.43 to get to the top. So it's going to take another 1.43 to get back down. So that's why we would double it. And because we're talking about horizontal range, there is no acceleration. So I don't need to use the first, second, or third kinematics equation. I can just use the simple relationship of distance equals rate times time. Now, technically, that is the first part of the second kinematics equation. We're just leaving off the 1/2 AT squared because there's no acceleration. So it's not like it's not related to kinematics equations, but I just, in my brain, I'm always thinking, oh, horizontal, no acceleration, so distance equals rate times time. The rate is the 24.2 meters per second we found using our trig, and the 2.86 seconds is double the amount of time it takes to get to the peak. So it would travel a horizontal range of 69.2 meters. And now we've found both the maximum height and maximum range for this projectile based on the given values. Questions? I went through that pretty slow because I wanted to make sure you could follow. I also wanted to show you all the different routes, or multiple different routes. I mean, not all the routes, but multiple different routes of how we could solve this one. So We'll go a little bit quicker on the last two examples. All right, so now we've got a second one. What is the hang time for a football kicked with an initial velocity of 25 meters per second at an angle of 60 degrees with the horizontal? So hang time is kind of a term we generally only use in soccer and football that I know of, trying to figure out how long the ball's in the air. For football, especially when it's punted, how long is the ball in the air? It's helpful for the special teams to know that value and to maximize that hang time. So it's just basically saying, what's the time of flight? What's the air time is another way to say it. But they often use that phrase hang time. So I want to make sure everyone understands what it means. So they've given us an angle. They've given us the actual velocity. We're trying to find the time of flight. Sally, do you have any idea what, if you were having to do this on your own, any idea where we could start? Just something to get us going here.
Well, to find the time, could we? No, we couldn't. We don't know the final velocity, or there's no equation we can plug it into to find the time, right?
Yeah, not quite yet. Yeah, so that's a good conclusion. We can't just jump right to the kinematics equations because there's nothing quite yet we can do. Evan, any ideas? Is there something we could do to so we could use those equations? Is there anything we could do to get us started?
Probably use sine to find the vertical velocity.
Okay. And why would that help?
Because then you can use that velocity to find the time, at least from that to the peak, and then you can double it.
Okay. So you're starting to think about a path here. All right, good. The key that I want to identify here in this little conversation is that basically the best place to start for all of these projectiles launched at an angle is go right to the trig. Because as Sally identified, there's not really an equation we can use straight off the bat. We need some more information first, and the trig is what's going to give us that information. So right away, I would just, even if we don't know if we need the horizontal and the vertical, I just generally find both. If you're really organized and you can streamline your thinking, you may recognize that you don't need both, but I just usually do them both. It doesn't take very long. And so if I take the hypotenuse of 25 times the cosine of my angle, that gives me the adjacent horizontal component. And if I take 25 times the sine of the angle, that gives me the vertical component. And because it's a steeper angle, my vertical should be larger and my horizontal should be smaller. They are, so I look like I'm probably on the right track. Now, Evan was saying we could find the time because now we know the initial velocity vertically is 21.7 meters per second. And we know the final velocity at the peak is 0. So that gives me 2 velocities. And Aiden, what's something else I know besides the 2 velocities vertically?
You know the acceleration due to gravity.
Yeah, so that gives me my 3 pieces. And I could right away go to VVAT. And from VVAT, I could find the time. And then I think Evan even said this, you could double the time and get your answer, right? Basically the same thing we did in the previous problem. But I'm not satisfied with that. I want to do it a different way. And main reason I want to do it a different way is because I want you to get into your mind that there isn't just one route. And I also want you to recognize something about the displacement that can be super handy in solving a lot of problems. If the ball goes up from the ground and comes back down to the ground, what's the vertical displacement?
0.
0. So I actually know the vertical displacement. I don't know the horizontal displacement, but I do know the vertical displacement, which means I know the delta x or delta y, if you rather use y since it's vertical. So I could actually use the second kinematics equation and solve this also. Not that it's better, but it's just another route. If I think about this second kinematics equation, the vertical displacement is 0. It starts at the ground and ends at the ground. It starts where it ended. And the vertical velocity is 21.7. The acceleration is -9.8. I have everything but time. And so I can also use this second kinematics equation, plug my numbers in, solve for t, and find that the time is 4.42. Now here's the question though. Is that the hang time, or do I need to double that? Any ideas?
That's the hang time, right? Because we use the displacement over the whole thing.
Yeah. If we're saying the displacement 0, we're not saying it's from the ground to the top. That wouldn't be 0. We're saying it's to the ground, to the top, and then all the way back down to the ground. So we're talking about the whole parabola. The displacement will be 0 for the whole parabola, where it started all the way up and all the way back down. And so since we're talking about the whole parabola, this is the time. We don't double it. If we use that VVAT route like we did in the first example and found the time to the peak, that's only half the time, because it takes that long to get to the top. It would take that much longer to get back down to the ground. Questions on example 2? All right, one last one. A running dog, I don't know if you heard my dog making noise in the background there a second ago, kind of timely. A running dog leaps with initial velocity of 11 meters per second at 30 degrees. What is the range? So now they're asking us horizontal information. So Andy, where can I start? What should I do to get the ball rolling here?
Well, you could start by finding the x and the y with the
Okay.
angles.
Yep, I know the angle, I know the hypotenuse. Just use my trig, find the x and the y. That's where I would start. So I draw my picture, I find my components. 11 is the hypotenuse times the sine of 30 is going to give me the vertical. And 11 times the cosine of 30 is going to give me the horizontal. And so that's where I would start, and I would figure out horizontal is going to be 9.53 meters per second. Vertical is going to be 5.5. 30-degree angle, so that makes sense. The horizontal should be bigger than the vertical since the angle is less than 45. All right, so I've started. I at least now know some components. Rocky, any ideas on what I could do next? There's not one way, but do you have any ideas on what we could try?
Try to solve for time with the first kinematics equation, I guess. I don't really know.
Yeah, I think that's what I would do. We know, and so if I'm using that strategy to try to find time, if I'm using VVAT, that first kinematics equation, I'm going to need to be thinking about the vertical, right? What's that? Yeah.
I was going to say I meant the second. I was
Oh.
thinking of, I don't know.
Okay. You can do it either way, actually. So if we use the second one, we would be saying we're using that delta x, or if you want to use y. And so we could use either method, and that's the magic of this. Both work fine. If we use VVAT, the only final velocity we know is at the peak. So we would be finding the time halfway. If we use the second kinematics equation, then we could find the time for the whole thing. So both work. I mean, it's not that hard to double your answer, right? If you use the VVAT method. If you use the second one, you don't have to double it, but so either one is fine. We know that y is going to be 0 at the peak. We know that the acceleration is negative 9.8. We know the displacement is vertically going to be 0 because it leaves from the ground and comes back to the ground. So we could use VVAT. We could use the second one. Here we're just showing the use of the second one. The vertical displacement, it jumps from the ground and lands on the ground. So it has a vertical displacement of 0. Its vertical initial velocity is 5.5 meters per second. And it's going to be accelerated because of gravity at a rate of negative 9.8 meters per second squared. So I just plug it into that equation like we did in the previous problem, solve for t. And that means the dog is in the air for 1.12 seconds. If there is an advantage to this strategy, It just is that because that displacement is from ground to ground, it's the whole parabola, so I don't have to double the time. If you went for VVAT and just went from the 5.5 initial velocity to the 0 at the peak, you would just be finding the time halfway and have to double it. Not that much harder. So now I know the time, but the question wants to know range. So how do I find the range? Okay, can you help me out? How would I find the range now that I know the time? Any ideas?
Well, if you know the time and the range is the distance traveled, right? Just from my vocabulary, yeah. So you could use the sort of, I don't know the name of it, but the equation that's like the displacement of x is equal to velocity 0 times time plus 1/2 acceleration times time squared. Find how long it's traveled.
Okay, good. And so if I use that second kinematics equation, this same one that we used for this step, but now I know the time, and then instead of using the vertical velocity, use the horizontal velocity, it would tell me the range. The key, if we use that whole equation, is to recognize that the acceleration horizontally is 0. So that whole 1/2 AT squared is just going to cancel out because there's no horizontal acceleration. And so basically it simplifies down to distance equals rate times time, or distance equals VOT. And the V is 9.53 from the trig that we did. We know horizontally it's moving at 9.53 meters per second. From the previous slide, we found out it's going to be in the air 1.12 seconds. And so our range horizontally is 10.7 meters. All right. Questions? All right. So that is it for today. Got about 30 minutes in class left. So if you need help with anything, maybe you need help with, oh, maybe I should keep sharing that in case people are still writing. Let me put that back up in case people need it. If you need help with anything, I'll keep the Zoom running the last 30 minutes. You can come and go, you can stay. I'll help with any questions you have, whether it's over the assignment. The assignment is worksheet 3. So you can work on that. You can do test corrections. Those are due tomorrow night. You may have other questions that you want to ask. I'll just be available the whole 30 minutes. If you don't have any questions, you're welcome to leave the Zoom and just, if you've printed it out, worksheet 3, and that's what you want to work on, you don't need to have the computer running. You need to be staring at a screen while you're doing it if you don't want to. So you can log out if you'd like. But if you need help, I'll be here. And if I don't see any more today, good to see you during class and look forward to seeing you next time. If you're sticking around, I'd be glad to help you out. So if you're taking off, I'll see you later.
Thanks, Mr. Webb.
Yeah.
Thank you.
Yeah.